So I want to start by thanking the organizers for organizing this wonderful series of online seminars that promote science and mathematics. And I'm very honored to have the opportunity to give a talk in the seminar series. So as we mentioned, I'm going to talk about reinforcement learning today, particularly trying to set up the comfort zone of just a vanilla Markov decision process kind of model and reinforcement learning, other machine learning paradigms, including federated learning and distributional robust optimization. So let me begin by telling you what reinforcement learning is. So unlike like supervised or unsupervised learning that is most well known in machine learning literature, reinforcement learning is sort of this different machine learning paradigm where agent tries to learn by interacting with the environment. And typically the environment is unknown to the agent, so that the agent actually need to sort of configure and trying to figure out what the environment is based on strong actions inside this environment. And the goal of the agent is also not to just maximize its immediate reward, but often it has some long-term reward in mind, and its goal is actually trying to maximize its long-term total reward through this lifetime interaction with the environment. So also characteristics make learning interesting, very unique, and particularly challenging. But nonetheless, we have been seeing a lot of stories of reinforcement in recent years from the being adopted and making a lot of different problem domains and chip designs. And recently, I think it will be useful helping us to even prove some mathematical theorem. So it's probably not exactly to think to claim maybe reinforcement learning is really very important and holds great promise to artificial intelligence. Really fully realize in practice. And tracking the research community and also myself is equal efficiency. So if you look at a lot of the success stories, training our agents takes a lot of the ability of maybe a simulator or generating model that allows you to almost requires reinforcement learning to succeed. However, this ability of collecting kind of data samples not a lot of real questions, particularly data collection very expensive.
Sorry,
also very tight.
So there may be some problems in the network. So can you try to So can you check the network quality, and do you have another choice?
Maybe get closer to the speaker and speak in a bit
maybe
slow way.
Let me try to change to a different
problem from the network connecting.
Yeah, let me try to change to a different ear plug. Yeah. Is this one better?
Yeah.
Yes, much better.
Okay, let me use this one. I think that's maybe an issue with the ear plug. Yeah, I need to get a new AirPods. All right, can you hear me now? Is this good? All right. So I was just talking about the issue of sample efficiency, that in a lot of applications, data collection may be very expensive or time consuming. This is especially problematic when the problem dimension is huge, when we are facing very complex environments with enormous data and action spaces. So this really calls for the design of more sample efficient reinforcement learning algorithms. Now, from a statistical point of view, in this talk, we'll be particularly interested in taking this kind of non-asymptotic analysis viewpoints. Now, if we step back a little bit and look at sort of how the theoretical landscape has developed in the last number of years, reinforcement learning has been actually been quite heavily analyzed even back in the 80s, primarily from maybe the control community, using tools such as ordinary differential equations, where the focus is trying to understand what we call the asymptotic analysis, trying to understand if you are giving, for example, unlimited number of iterations, unlimited data samples, whether the algorithm indeed produce the quantity of interest, such as the optimal policy or the optimal value functions. Now, this kind of asymptotic viewpoint is nice because it gives us this kind of proof of concept in terms of the correctness of the algorithm. However, it does not really deliver fine-grained information about the speed of the convergence of the algorithm in finding the optimal solutions. And in order to sort of delineate this kind of speed information, there has been a lot of efforts in recent years trying to understand sort of the non-asymptotic performance analysis, thanks to the availability of tools developed in the literature of high-dimensional statistics and high-dimensional probability. And with the availability of this kind of non-asymptotic analysis that can fully delineate all the problem dependencies with salient problem parameters, we can really sort of pin down the sample complexity requirement of a lot of reinforcement learning algorithms and fully really understand the statistical efficiency of these algorithms that are applicable to modern practice of reinforcement learning. Particularly in recent years, there has been this surge of understanding the sample complexity reinforcement learning in the standard model of Markov decision process, which is sort of this canonical model to model the interaction between an agent and the environment. And this sort of Markov decision process is sort of very well formulated mathematical model and has been serving as this playground for people. So before I jump into the more technical part of the talk, let me just quickly review what this Markov decision process is. And for many of you, this may be something that you are already familiar with, but please bear with me so that we can just make sure everyone is on the same page. So what is this Markov decision process? As I mentioned, this is sort of the model used to characterize interaction between agent and environment. And we're going to model the environment using some sort of a state space. And each element in the space tells you configuration of the environment. And we're going to model the sort of the actions of the agent using some action space. So each element in the action space tells you a possible action the agent can make to interact with the environment. And upon receiving an action from the agent, the environment will push a reward to the agent. And the reward is a function of the current state and the current action. And for the sake of the talk, we're going to think of the reward is normalized in an interval from 0 to 1, which is something you can always do. And the goal of the agent is actually trying to design what we call a policy. And this policy is essentially a probability distribution over the action space for any given state. So for any configuration of the environment, the policy tells the agent what it should do. And in general, this could be a random action selection rule. So it's a probability distribution, but you can also take a sort of deterministic action selection rule by just fixing which action you are going to take for a given configuration of the environment. And of course, the crux of the problem is that the environment is sort of uncertain, so that it will be sort of changing over time. And the way the environment is going to evolve is specified by this sort of transition kernel, so that we know after this one round of interaction, the environment will move to the next state, which is drawn from this probability distribution over the state space, given the current state and the current action. So usually this transition kernel is sort of the elephant in the room because it has a huge dimensionality compared to the other quantities in this problem. All right. So as I mentioned, the goal of the agent is trying to sort of design this policy And in order to design the policy, we first need to find a way to evaluate the goodness of a policy. And this comes to the notion of value functions that allows us to evaluate a policy. So imagining we have this Markov decision process, and we're initializing the environment as some initial state S, and from that initial state, our agent will be pulling actions based on this policy pi, and generating a trajectory in this Markov decision process. And along the trajectory, the agent will be also collecting a rewards. So the value function is actually defined as a total sum of these rewards, where future rewards are discounted by a factor of gamma, indicating more nearsighted rewards carry a higher value to the agent. Similarly, we can define the Q function. The Q function is defined a little bit different from the value function in the sense that besides fixing the initial state, we are also going to fix the initial action to be arbitrary. And after the first actions, the rest of the actions will be pulled based on the policy pi. So the Q function has an extra degrees of freedom compared to the value function. And both of these quantities are very important in reinforcement learning. So let me just recap what this parameter gamma is also very important. It's what we call the discount factor in the problem. So roughly speaking, if you sort of take this sort of geometric sequence over this infinite sum, this number 1 over 1 minus gamma is can be thought as sort of essentially the effective horizon, in the sense after this time step, you can kind of do a truncation and throw out the rest of the rewards because their value basically carry very little sort of weight in your total calculation of the value function. So often this number 1 over 1 minus gamma is kind of an important quantity in this kind of infinite horizon problems that also allows you to do kind of back of the envelope kind of translation between finite horizon setup results with infinite horizon results. All right. So again, now we have these value functions. We can formally define the goal of reinforcement learning is essentially trying to find the optimal policy that maximizes value functions. Now, when the environment is known, this is actually a well-known problem that has been solved by classical literature in dynamic programming and optimal control. Now, in reinforcement learning, we are particularly interested in solving the problem when the environment is actually unknown and need to be configured while figuring out the right policy. A little bit of notation in this talk, whenever I'm referring to something that's optimal, I'm putting a star on my value function, Q function, and policy. So that whenever you see a star, you know we're talking about the optimal quantity, which is a target quantity of interest. All right. So typically there are two types of approaches to reinforcement learning, a model-based one and a model-free one. So in a model-based approach, which is also called a plug-in approach, based on the samples we are collecting from the environment, we'll actually try to first construct an empirical model, an empirical estimate of the model. For example, this can be done based on using a maximum likelihood estimate of the model. And once we have the model, we can go back to the literature of dynamic programming and use classical planning-based algorithms to find the optimal policy and the optimal value functions. On the other hand, we have also this model-free approach, which is kind of the signature approach in reinforcement learning that directly bypass this step of model estimation and trying to estimate directly the quantitative interest, such as the value function and the policies. Because the value function and the policies typically has a lower dimension compared to the size of the model, at least by a factor of the size of the state space. Model-free approaches are typically more memory efficient. They're also usually more adaptive to changes in the environment. So they are very popular in practice. Now, both type of approaches has been studied quite actively in recent literature. So let me just give you two results that we had in the past work that I thought are kind of interesting to share. So the first one is about this model-based approach. So in fact, we've seen that if you take this standard MDP, for example, you collecting data using generative models,
we've actually seen that based on sort of a sequence of recent work, people have established that if you take this sort of model-based plug-in approach, it is actually minimax optimal in the sense no other algorithm works better than this model-based approach, and its performance already hits this minimax lower bound, which sort of scales on the order of SA 1 divided by 1 minus gamma epsilon to the third order times epsilon square. On the other end, somewhat surprisingly, if you take a sort of model-free approach, for example, if you take this probably most popular algorithm called Q-learning in the literature to solve the same problem, in fact, the sample complexity of Q-learning is probably suboptimal by a factor of the discount horizon compared with a minimax lower bound, which we already mentioned that can be met by a model-based plug-in approach. So this sort of suggests there is this probable gap between a model-based approach and model-free approach in terms of sample requirement. We're not getting into details of this type of results, but this kind of highlights the message we mentioned earlier that if you take a non-asymptotic lens, this kind of fine-grained sample complexity analysis really allows you to tell the difference between these different approaches that both converge asymptotically. But in fact, there is a huge difference in terms of their rate of convergence. And this can be particularly important in practice when you have long horizon problems. So this again highlights this importance of leveraging this non-asymptotic toolboxes to understand the sample efficiencies. Now back to sort of what we want to do in this talk. We want to be able sort of getting out of this comfort zone of analyzing standard Markov decision process, because as I mentioned a little bit, there has been actually a lot of recent work in understanding the standard paradigm, and there's some sort of good understanding about the sample efficiency of different approaches in the standard paradigm. In this talk, we want to kind of go beyond the paradigm standard MDP models and trying to bridge with other sort of machine learning models that are sort of very popular and useful in practice. So what in the first part of the talk, I'll be focusing on its connection to federated learning, particularly understand how we can leverage the paradigm of federated learning to help us to train a reinforcement learning agent more efficiently. In the second part of the talk, I'll try to bridge with this literature, distributional robust optimization and the learning, and trying to bridge this well-known sim to real gap, addressing the issue when the data that when we train a sort of IO agent in some sort of idealized simulated environment, but when we want to sort of execute in practice, there's often this inevitable gap between the real environment and the simulated environment. And how do we make sure the trained environment can still succeed in the real environment, leveraging this tool of distributional robustness? All right, so without further ado, let me directly jump into the first part of the talk, which is trying to leverage reinforcement learning with federated learning. And this is joint work with my wonderful student, Jin Wu at CMU, who is co-advised by me and my colleague, Gauri Joshi. And this is based on paper that will be presented later this month at ICMO. All right. So what is federated learning? Federated learning is sort of has been very popular in the maybe last 10 years-ish. And the way this sort of machine learning, federated learning paradigm works is leveraging sort of the use, if we have some maybe server, we can actually leverage the server to coordinate some training of global machine learning model using local data from sort of a cluster of users or devices, where these devices may have their own local data, but they will never move the local data to the server. But the server will sort of coordinating this model updates between the server and the clients, so that we can sort of elevate the need of data by leveraging this local data available as the users. And in fact, federated learning has already been adopted in many companies and sort of real world products. For example, Google, IBM, Apple are all using federated learning to help us train models from multiple data and user data in order to improve the performance of their products. So the natural question is, can we actually harness the power of federated learning for reinforcement learning? A lot of this sort of advances I mentioned about federated learning is in fact most about supervised learning. But there has been actually very little work for leveraging federated learning for reinforcement learning. So how do we do this? From a conceptual perspective, this seems to be quite straightforward, at least in terms of sort of the formulation we are envisioning. So imagining that you maybe have some sort of server that helps you to coordinate the training of this reinforcement learning agent. And I may have multiple, maybe local agents. And each of these local agents may be collecting data on its own, possibly using its own sort of behavior policies, its own way of interacting with the environment. And based on the local data we are collecting, we want to be able to sort of pull this data together, but in sort of virtual way, because we are not never going to move the data to the server, but we want to sort of leverage the maybe locally trained models or policies or value functions in sort of a collaborative way without sharing the data set. Hopefully by doing so, we can sort of reduce the data requirement in terms of the amount of data is required by a single agent in training the reinforcement learning model. So in particular in this talk, we'll be taking just one algorithm, the Q-learning algorithm, this model-free algorithm, and trying to understand whether we can sort of probably accelerate the learning of this algorithm in this federated setting. We're going to ask and trying to answer the following questions. The first question is a natural one about linear speedup, which is typical in this kind of federated setting, is if you have maybe multiple agents, can you actually sort of trim the training time by the amount of agents you have? This is a so-called linear speedup, and we want to see if we can achieve the same kind of linear speedup for reinforcement learning. There is also the question of communication efficiency. Now, in federated learning, it's very typical that we will want the agents or the user to do multiple updates, multiple local updates, such as multiple steps of stochastic gradient descent before it shares its model update with the agent in order to save communication. Because communication is typically a bottleneck in this kind of federated settings, we want to do kind of similar thing. Can we actually also do multiple local updates in our update of the Q function before we do communication with a server in order to save communication? Finally, there is this interesting question about heterogeneity, which is a little bit from the typical notion in federated learning, but nonetheless, here we are talking about heterogeneity of the local behavior policies, because the local agents can be running very different behavior policies. How does this heterogeneity in the local behavior policies impact the training performance? All right, so with these questions in mind, let's jump into how the algorithm is being formulated. So as I mentioned, we're going to look at this Q-learning algorithm. And this is sort of classical algorithm, which is nothing but a stochastic approximation mechanism to solve the so-called Bellman equation, which is sort of the foundation of dynamic programming that tells us sort of this optimal Q function is actually the fixed point of the Bellman optimality operator. And this Bellman optimality operator is defined in the sort of the bottom of the slide, which is kind of basically a bootstrapping way to help you to improve the quality of the Q function estimate based on a combination of the immediate reward and also a discounted reward. So the discounted sort of best value of the next state. And in order to evaluate the Bellman's optimality operator, you can see that you actually need information about the model. And this is what we do not have in sort of reinforcement learning setting, because we do not have immediate access to the model information, but rather we have to actually leverage tools such as stochastic approximation to get stochastic variant of the Bellman's optimality operator and solve this in a stochastic way. And we're going to look at the so-called asynchronous Q-learning. So imagining we we are sort of collecting data in this Markov decision process following some behavior policy pi b, which you do not need to know what this behavior policy is when running the algorithm. But given a trajectory in the Markov decision process, this asynchronous Q-learning algorithm will essentially do the following. At every time t, it will try to update one entry in the Q table as a state action pair it is currently visiting. And the way it's updating this entry is taking a convex combination of the old data, the old value, and sort of the new value based on a stochastic approximation of the Bellman's optimality operator, calculated using the current information at the current state action pair you are visiting. So if you compare this stochastic version of the Bellman operator with the population one, you see that essentially we are dropping this expectation over the possible realization of the next state, but just using the next state we actually visit in this trajectory. And the sort of the width of this convex combination is determined by the learning rate eta, which is something we are going to determine in the algorithm. All right, so this sort of give you sort of the understanding of the standard algorithm, this asynchronous Q-learning algorithm, which is essentially an algorithm where as you run along the trajectory, every time you just update one entry in this two-dimensional state action Q table, and you're kind of jumping around different entries in the Q table and updating it. The question is how to actually do this in this federated setting. As we mentioned, in this federated setting, we're going to have a bunch of agents, right? And each agent is going to actually having its own behavior policy. And each agent will actually trying to execute this Q-learning update rule on its own without picking at other agents' data. And as we mentioned, we're interested in this kind of local updates paradigm. So every agent will actually run, say, tau rounds of local updates before it sends its update to the server. So when it sends the data to the server, it will send the Q table to the server. And the server, when it receives all the Q tables from all the agents, it will just do an averaging of the Q table it receives from all the agents. And then once it calculates this average, it will push this back to all the agents. And then the agents will pick up and run this local updates again. All right. So for people who are familiar with this kind of with federated averaging in federated learning, you can see this is pretty much federated the typical steps of federated averaging, except that now we are doing this for Q-learning. So we are doing this multiple local updates and averaging and return the estimates back to local agents and do multiple local updates again and averaging again, so on and so forth. So since we very natural algorithm, can we actually achieve faster convergence when we have this heterogeneous local behavior policies with low communication complexity? So sort of hitting all the targets we want to achieve. Now, before our work, there's actually some previous results in this literature. So let me say a little bit about what has been achieved in the past. One of the key quantity in understanding the performance of these algorithms is this sort of minimum state action occupancy probability, what we call mu min. So on average, every behavior policy induces some sort of Markov chain over the state action pairs. And the stationary distribution of this Markov chain is very important. It's what we call this mu pi b's. And the sort of the minimum entry determines the bottleneck of our performance, because that tells us which entry we are visiting the list, and we need to sort of visit it more in order to get a good estimate of the Q function in that entry. So this mu min turns out to be a bottleneck in the performance. And one of the sort of the only work before ours by Kodadadian et al. Actually get a sample complexity that look like this on the order of I squared divided by K mu mean to the 5th order times some factor of the discount factor and epsilon square. So the nice thing about this result is actually we see this factor of k in the denominator, indicating as you have more and more agents, the sample complexity indeed get to enjoy this linear speed up behavior. On the other end, if you try to benchmark this sample complexity with the sample complexity we know for the single agent case when k equals 1, where you see there is actually a huge gap in terms of dependencies with other parameters, such as the size of the state space, the dependency on mu mean, and the effective horizon. In fact, if you look at when this sort of linear speed up really becomes beneficial compared to the single agent results, this benefit only becomes effective when k is much larger than this astronomical order. And because mu mean is at least or at most 1 over SA, so this actually is on the sort of polynomial factors of the size of the state space, which is really, really huge. So a natural question is, then can we actually improve the dependency on the salient parameters? Try to close this gap to make the benefit of linear speed up more apparent, even when k is small. So fortunately, the answer is yes. So in our ICML paper, we actually have this sort of improved sample complexity analysis that shows that if you take this sort of federated asynchronous Q-learning algorithm, the algorithm actually gets to epsilon accuracy when the sample complexity is on this order, where we see this linear speed up in the denominator k, and we also improve the dependency on mu mean to the just the linear order in the denominator, as well as improving the dependency on the effective horizon. And we introduced this new parameter that is actually hasn't been realized in the prior analysis that we call this heterogeneity parameter. And this parameter is essentially trying to measure the heterogeneity of different behavior policies in terms of their stationary distribution. So that you're looking at the worst case behavior policy versus the average behavior policy. And this parameter is always going to be bounded between 1 and 1 over mu mean. And if you have, for example, local behavior policies to be very similar, so this heterogeneity parameter is close to 1, then we can actually get a near optimal linear speed up. So putting all these things in figure, we see that when this heterogeneity parameter is small, our result is actually very closely matching the single agent Q-learning sample complexity up to a factor of the effective horizon. So suggesting that this result is nearly tight with respect to other parameters, except probably just one factor with effective horizon. And this is significantly improved over the prior art. All right, so far so good. But if you look at a little bit deeper about the result, it seems that it's not that positive a message in the sense that if this heterogeneity parameter is very large, the performance actually degenerates, suggesting that if you have multiple agents that are very dissimilar, performance actually may be worse than when you're just using a single agent. But on the other end, because this result actually leverages this mu mean quantity, it requires this mu mean to be strictly greater than 0. It in fact requires all the agents cover the entire state action space. And this may be somewhat stringent. After all, the benefit of leveraging multiple agents is trying to alleviate this kind of requirement. For example, imagining if you have multiple agents, but each of the agents may only explore a subset of the environment, but maybe collaboratively, they cover the entire environment. We may still imagining learning is possible in this situation, even though none of the single agent can learn the environment by itself, but collaboratively, they should still be able to learn. But this is not sort of uncovered by the current paradigm. So the question is it possible to actually elevate this kind of full coverage requirement and really tame this heterogeneity requirement as well? A key observation is to realize that if you have multiple agents, but they may be emphasizing different parts of the environment in their sort of behavior policy, when you are trying to aggregating their updates, you really shouldn't be aggregating their updates in a sort of equal weighted manner, because not all these updates are of the same quality due to this sort of limited visits. But rather, when you are averaging them, you want to put higher weights to the visits that are sort of based on sort of the frequency of the visits. So if agent 1 has higher confidence, maybe in this part of the environment, then we should assign higher weights to agent 1 for this part of the environment in its local updates. So this motivates us to develop this so-called importance averaging mechanism. When we are updating the Q functions, we actually assign this importance weights, this alpha T's. And these alpha T's are calculated using sort of the number of visits in the synchronization period by each of the agents. So this added a little bit of overhead in terms of communication costs, but this allows us to significantly improve the quality of the Q function updates. So I will now get into the detail of this formula. This is essentially motivated by the analysis and the way the Q function updates rule is constructed. If you're interested in the details, you can look at our paper. And with this importance averaging, we can actually now get improved sample complexity result that shows that in order to reach epsilon accuracy, now the sample complexity actually scales as order of 1/k times mu averaging, where we maintain the linear speed up in the denominator. But importantly, we actually replace the mu mean by this so-called mu average, which is actually the minimum entry in the average stationary distribution of all the behavior policies. And this quantity is probably larger than mu mean and only requires all the agents to collectively cover the entire state action space. We also eliminate the heterogeneity parameter on the numerator so that the performance becomes actually independent. It no longer suffers from the heterogeneity of the behavior policies in the performance. So if you put these two factors in this picture to compare the sample complexity in the case of equal averaging versus importance averaging, we see there is two important benefits of importance averaging. One is a change of mu mean to mu average so that we alleviate the coverage requirement. The other is the elimination of the heterogeneity parameter in the sample complexity. So the performance becomes less sensitive to the heterogeneity of the behavior policies. So all in all, we see that this importance averaging mechanism indeed greatly helps us to improve the performance of this federated Q-learning algorithm. And it's an important mechanism that also actually not only of theoretical interest, but in the paper, we also show some numerical results that show that indeed importance averaging also helps in practice to improve the learning quality. So just as a quick recap of this first part of the talk, we see that by leveraging this federated learning paradigm, we actually get some provable benefits in terms of achieving near optimal linear speed up in the sample efficiency, so that with the help multiple agents, we can probably speed up the learning speed by essentially a factor of the number of agents in the problem. And we are still actively working on this direction. For example, examining other problems in reinforcement learning, such as policy evaluation and offline RL, as well as in the sort of multitask setting, where maybe different agents can also have actually not only heterogeneous policies, but also heterogeneous environments. So because of time, let me now quickly jump to the second part of the talk, and I can answer any questions that you may have towards the end of the talk. So in the second part, I want to look at reinforcement learning with distributional robustness. And this is joint work. Sorry, I think I made a typo here in the name. This is the first author is actually Lacy Shi. And she's actually a student at CMU working with me, but is graduating very soon and going to join Caltech as a postdoc. And this is also with my colleague at UPenn and also our collaborator, Matthew Geist at Google. And this paper is available on arXiv. All right, so the reason we're interested in this sort of distributional robustness is because of the increasing need to address safety and robustness reinforcement learning. And as we all know, when we are training a reinforcement learning, we often rely on the availability of some simulated or training environment. For example, maybe you are playing this game of Mario Kart, and maybe you are driving this vehicle on a sunny day, but during testing time, you may be driving this vehicle in a raining day where the environment will be different from the environment you are facing during training. And this kind of simulation to real gap is actually causing some severe degradation in the performance of reinforcement learning agents. If you are just leveraging a standard training algorithm. So the natural question is, can we actually learn a policy that not only achieving good performance, but also are robust to perturbations in the model parameters? So to address this issue, there has been a recent line of work trying to leveraging the approach in distributional robust optimization literature. So in order to do so in sort of reinforcement learning setting, we need to first introduce how we model the uncertainty in our transition kernels. So imagining that you have some sort of nominal transition kernel. For example, this is the environment that you use in training. But during execution, the actual environment may be a slightly perturbed version of this nominal kernel. So the actual kernel P that you see may be different from the nominal kernel. But hopefully their deviation is not too large so that you can actually measure this deviation by using some divergence rho. And this divergence is maybe bounded by some uncertainty level sigma. And in practice, in this formulation, we actually want to consider all the possible transition kernels as long as its distance from the nominal kernel is bounded by this uncertainty level sigma. So this gives us this kind of worst case modeling that we can actually tolerate any adversarial perturbation in the transition kernel as long as this perturbation size is bounded by this level of sigma. And typically, we can take our divergence rho sort of as any choice of our favorites, but typically we can take this, for example, as some sort of F divergence, like TV distance, chi-square divergence, Cal divergence, and so on. Now, given that we are now looking at sort of not only one transition kernel, but a family of transition kernel in this uncertainty set, a natural thing to look at in terms of evaluating the goodness of policy is actually look at the so-called robust value function or Q functions, which actually still look at the standard value function for any kernel P, but drawing from this uncertainty set. And we're going to take the smallest possible value function for the transition kernels in this uncertainty set. So in other words, we are actually measuring the worst case performance of the policy for all the transition kernel in this uncertainty set. So guaranteeing that the performance of this policy shouldn't be too bad. And this naturally gives us our goal in this kind of distributionally robust MDP settings. That is trying to find the policy pi star that actually maximize these robust value functions. So in other words, we want to find the policy so that the worst case performance is not too bad. So this is a little bit pessimistic, but and also conservative. But nonetheless, if you care about safety, this may be the best thing you can hope for. Luckily, there has been this sort of pioneering work by Ignar and Elim and Gowry that shows that a lot of the classical tools in dynamic programming actually can be carried over in this kind of robust MDP setting. For example, we have our robust Bellman optimality equations that actually carry over a lot of nice properties of the standard Bellman's optimality equation. And we can similarly run value iteration algorithm, but now in this robust settings, distributionally robust value iteration that carries over a lot of nice properties of standard value iteration algorithms. So if you want to understand performance of robust MDPs in these settings, we can take this sort of sampling mechanism that kind of similar to the generative model setting, but now we are drawing samples from this nominal transition kernel. But during learning, we actually want to learn for this robust MDP so that we want to make sure the learned policy is actually robust. A natural question is how does this benchmark with the standard MDP? If you are drawing samples from this sort of nominal transition kernel and say you build this model-based approach, this empirical MDP, one way is that you just learn the optimal policy for the nominal kernel that give you the results for the standard MDP. But you could also alternatively try to learn the robust policy around the nominal MDP by leveraging the model-based approach for robust MDP. Well, it seems the second approach, when you try to learn robust policy, give you additional robust properties. But nonetheless, there may be a premium you need to pay in terms of sample complexity requirements. Actually, is it harder to learn a robust policy? Do you require more samples if you want to learn a robust policy compared to learning in a standard MDP? Now, this question is actually hasn't been addressed in the prior literature. So for the sake of the time, let me just look at the case with total when the uncertainty set is taken as a TV distance. In this case, we have actually some prior results that give you some sort of upper bound, and also some results give you the lower bound in terms of sample complexity requirement. You can see that this upper and lower bounds actually has a huge gap in them. Moreover, if you try to compare them with the sample requirement of standard MDP, it's actually lying in the middle, so that it's actually not clear how to benchmark the sample complexity requirement of robust MDP with respect to standard MDP due to this huge gap in existing results. A similar gap also appears actually when you take the chi-square uncertainty set, where again you see the sample complexity existing results again exhibit this very large gap where they kind of sandwich this sample complexity of standard MDP, so that it's very challenging to actually benchmark the results. I should mention that the x-axis is actually plotting the uncertainty level. So when the uncertainty level is small, we expect the sample complexity of robust MDP should be the same as standard MDP. But as we sort of increase the size of uncertainties, how the sample size scales as a function of the uncertainty set is actually the most interesting question in understanding robust MDPs. So given all these gaps, it's actually a very open question about the sample complexity of robust MDP. And we try to answer this question in our work. Due to time, let me just talk about the result for the TV uncertainty set, because the result here is probably the most clean one. In fact, we pin down the mini-max sample complexity in this case, which is actually on this order of SA divided by 1 minus gamma to the quadratic order times the max of 1 minus gamma and sigma times epsilon square. And we also develop a matching lower bound, so that this actually establishes the minimax optimality of this model-based approach for RMDP under this TV uncertainty set. So if you draw this in the figure, and this is actually sort of this line here is our result, and you see that we actually have matching upper and lower bounds, and you see that when the uncertainty level is small, the sample complexity robust MDP essentially matches the sample complexity of standard MDP. But as we increase the uncertainty level, actually the sample complexity requirement becomes smaller, and it's actually probably smaller by a factor of the effective horizon when the sigma is very large, so that it's suggesting robust MDP are actually easier to learn than standard MDPs when you take an uncertainty set as a TV. Now, in the case of chi-square, I won't get into the details, but the interesting message here is, in fact, there are scenarios of the uncertainty set, and in some regimes, for example, when the sigma is taken as order 1, we actually have matching upper and lower bounds, and this result is actually probably larger than the sample requirement of standard MDP. Another interesting regime when you use chi-square divergence is as the uncertainty goes to infinity, the sample complex actually grows unbounded as a linear function of the uncertainty level sigma, suggesting that the problem can become much, much harder to learn compared with standard MDP. So in these cases, the message is actually opposite as a TV case, where robust MDPs can become much harder to learn than standard MDPs. Now, in this case, there is actually more work to do because we didn't really fully close the gap between the upper and lower bounds. There actually still has a gap up to some polynomial factors of the effective horizon. But still, there's this very interesting messages in terms of the hardness of RMDPs when you use chi-square divergence to measure the uncertainty. So with this, let me quickly sum up the second part of the work. The main message in the second part is trying to highlight when you add in this actual consideration of robustness in designing the IL policies, the price of the robustness is actually quite subtle, and it depends on the choice of the uncertainty set in terms of the your choice actually can has a quite important consequence on the sample requirement of the problem. And sometimes the sampling requirement of RMDP can be smaller than standard MDP, and sometimes the sampling requirement RMDP can be larger than standard MDP. So this message we find actually is quite surprising. And this motivates us to work on some future directions. For example, understanding other choices of the uncertainty set and trying to leverage function approximation in these results. So as a final conclusion, concluding remarks to this seminar, I hope I have at least conveyed, convinced you to some extent that there's actually a lot of interesting questions we can answer, delineating sort of fine-grained messages about the performance reinforcement learning algorithms by resulting to this kind of non-asymptotic analysis tools using high-dimensional statistics. And this message is not only having values in theory, but also help us to shed light on their empirical success and failures. So with this, I will conclude. And if you are interested in some of the papers I mentioned in the talk, you can find them on my homepage. And I want to thank you very much for your attention in the seminar. I'll be happy to answer any question you have.